This is a recast of the 7,800-word piece, Meta-Learning, from Schneepat.com. This article is about the concept of meta-learning in machine learning, its applications in various domains such as healthcare and finance, different types of meta-learning techniques, and its potential to improve the efficiency and effectiveness of machine learning models. Let's listen in.
Today, we're diving into the world of machine learning and specifically focusing on a technique called meta-learning. Machine learning is a subset of artificial intelligence where computers learn from data and improve their performance over time without explicit instructions. It's been applied to various fields, including healthcare, finance, and recommendation systems.
That's right. Machine learning has become increasingly important in different domains due to its ability to revolutionize complex processes and generate valuable insights. In healthcare, for example, machine learning techniques are used to diagnose diseases, predict patient outcomes, and personalize treatment plans. Similarly, machine learning algorithms are employed in finance to detect fraudulent activities and identify patterns in stock market data. And of course, we've all experienced the personalized recommendations made by recommendation systems on streaming platforms or online retail sites.
Absolutely. And one category of machine learning techniques that stands out is meta-learning. Meta-learning focuses on analyzing and learning from multiple instances to improve the performance of future learning tasks. It generates meta-knowledge or metadata by extracting features from various learning tasks, which helps guide the learning process by providing insights into which algorithms or models are most suitable for a given task.
That's right. Meta-learning allows for a more efficient and proactive approach to learning new tasks. By learning from past experiences, meta-learning algorithms can adapt to new tasks more quickly, making them highly advantageous in scenarios with limited training data or where the environment is constantly changing. They've shown promising results in recommendation systems, computer vision, and natural language processing.
Understanding meta-learning is crucial for advancing machine learning techniques. Meta-learning refers to the process of learning how to learn. It involves developing algorithms that enable machine learning models to become more efficient at learning new tasks and adapting to new environments.
Absolutely. Meta-learning algorithms aim to optimize the learning process itself by learning from past experiences and generalizing that knowledge to new situations. This is particularly helpful in addressing the problem of catastrophic forgetting, where models tend to forget previously learned tasks when learning new ones.
Right. And one approach to meta-learning is the use of meta-features, which are descriptive characteristics of the learning algorithm. These meta-features provide information about the algorithm's behavior and performance across different tasks. Another common technique is the use of metadata, which involves collecting and analyzing information about the training data or the learning algorithm's performance on previous tasks.
By utilizing this information, machines can effectively select and configure learning algorithms to optimize their performance on new and unseen tasks. Meta-learning plays a crucial role in improving the efficiency and effectiveness of machine learning algorithms.
Absolutely. Meta-learning holds great promise in advancing machine learning models and paving the way for future advancements in the field. It allows for more efficient learning, adaptability to new tasks, and generalization across different domains.
And it's not just about improving machine learning models. Meta-learning has real-world applications that directly benefit society as a whole. The healthcare industry can benefit from more accurate diagnoses and personalized treatment plans. Finance can benefit from better fraud detection and investment optimization, and transportation can benefit from improved traffic management systems and autonomous vehicles.
That's right. Machine learning has become an indispensable tool in addressing complex problems across diverse domains. And with meta-learning, we have the potential to further enhance these techniques and realize artificial general intelligence.
So in conclusion, understanding meta-learning is essential for developing more efficient, flexible, and robust machine learning techniques that can rapidly learn new tasks with minimal data and generalize across different domains.
Absolutely. Meta-learning techniques have a clear purpose, which is to enhance the learning process itself. By optimizing and improving the algorithm used in machine learning, meta-learning techniques can lead to more efficient and accurate predictions.
That's right. And one of the benefits of using meta-learning is improved model performance and generalization. These techniques enable the model to adapt and learn from various tasks and domains, enhancing its ability to perform well on new, unseen data.
And that's not all. Meta-learning also allows for the efficient transfer of knowledge and experience between different tasks. This reduces the need for extensive training on each individual task, saving time and resources.
Exactly. Meta-learning techniques play a crucial role in advancing machine learning algorithms, enabling intelligent systems to learn and generalize from diverse tasks and data. It's an exciting field with a lot of potential.
Now let's talk about how meta-learning compares to traditional machine learning techniques. Traditional machine learning techniques focus on building models that can predict the output for a given input. They require large amounts of labeled data for training and are generally designed for specific tasks.
In contrast, meta-learning is all about building models that can learn from a collection of similar tasks. This allows them to adapt quickly to new tasks and generalize well. Meta-learning leverages the knowledge gained from previous tasks to facilitate learning across new tasks.
And while traditional machine learning techniques require carefully designed features and optimization algorithms, meta-learning algorithms can automatically generate useful features by learning from multiple related tasks. It's a more efficient way of learning.
Overfitting and generalization issues are also critical challenges in machine learning techniques, including meta-learning. Overfitting occurs when a model learns the training data too well, making it perform poorly on new, unseen data. On the other hand, generalization issues arise when a model fails to capture the underlying patterns in the data and exhibits poor performance on both the training and testing data. To address overfitting, regularization techniques such as L1 and L2 regularization can be used. These techniques add penalties to the loss function to prevent the model from becoming too complex. On the other hand, addressing generalization issues involves increasing the amount and diversity of training data or refining the model architecture to better align with the data distribution.
Absolutely. Now let's talk about computational complexity and resource requirements. When implementing machine learning techniques, it's important to consider the efficiency of the algorithm in terms of computational complexity. This determines how fast it can process and analyze large amounts of data. Complex algorithms often require significant computational resources, including processing power and memory. So the choice of algorithm can have a significant impact on the feasibility of a machine learning project, especially when working with limited computing resources. It's also important to consider resource requirements when training and deploying machine learning models. Training deep learning models, for example, can be computationally intensive and may require specialized hardware, such as graphics processing units, GPUs, or tensor processing units, TPUs.
That's a great point. Finally, let's discuss the lack of interpretability in meta-learning models. Meta-learning models are highly complex and often involve multiple layers of abstraction, making it difficult to understand the reasons behind their decision-making processes. This lack of interpretability poses several problems, such as the inability to explain the reasoning behind a particular prediction or to understand the underlying features that are being used by the model. This limitation hinders the trust and adoption of meta-learning models in critical applications such as healthcare or finance, where interpretability and understanding the decision-making process are crucial.
Efforts have been made to develop interpretability methods for meta-learning models, including visualizing the learned representations or extracting importance weights for features. But more research is needed to comprehensively address this challenge. To sum up, meta-learning is an important subfield of machine learning that focuses on finding optimal learning algorithms for a given task or set of tasks. It enables machines to learn from past experiences and adapt to new tasks more efficiently. However, there are limitations and challenges that need to be considered, such as transferability issues, overfitting and generalization problems, computational complexity and resource requirements, as well as the lack of interpretability in meta-learning models.
That's right, Avery. Meta-learning holds immense promise for the future of machine learning. One key area of future potential lies in the exploration of more advanced meta-learning algorithms and techniques. As the field progresses, researchers are likely to develop more efficient and effective ways of learning higher-level meta-knowledge, which will enable improved generalization across different tasks and domains. Additionally, current research in meta-learning is focusing on developing methods that can handle non-ID data, where information is distributed unevenly across different tasks. By addressing this challenge, meta-learning algorithms have the potential to be applied in a wider range of real-world scenarios. This means that meta-learning can become even more adaptable and applicable in various industries.
Absolutely, Ben. Another emerging trend in meta-learning is the use of deep learning architectures for meta-learning tasks. Deep learning models, such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs, have shown remarkable success in various machine learning tasks. Now researchers are exploring the potential for meta-learning as well. By leveraging deep learning architectures, meta-learning algorithms can learn higher-level representations that capture more abstract and complex patterns. This leads to improved generalization and transfer learning capabilities. For example, deep meta reinforcement learning, DMRL, uses deep neural networks to learn an efficient representation of the meta policy that can adapt to new tasks quickly. This approach has shown promising results in achieving high performance on various reinforcement learning tasks with minimal fine-tuning.
The application of deep learning to meta-learning is an exciting area of research that holds great potential for advancing the capabilities of meta-learning algorithms. It opens up new possibilities for developing more intelligent and adaptive systems. Moving on to current research areas and open challenges in meta-learning, one important research area is developing more efficient and effective algorithms for meta-learning. This involves exploring techniques such as deep neural networks, reinforcement learning, and optimization algorithms to enhance meta-learner performance.
Exactly, Ben. Researchers are also investigating methods to handle large-scale meta-learning problems by devising distributed and parallel computing frameworks. This is crucial for scaling up meta-learning algorithms to handle real-world scenarios with vast amounts of data. Another open challenge in meta-learning research pertains to generalization. While meta-learning algorithms demonstrate superior transfer learning abilities, they often struggle with generalizing to new, unseen tasks. Addressing this challenge requires investigating novel strategies for capturing task relationships and developing more robust algorithms that can effectively generalize to unfamiliar tasks.
That's right, Avery. Furthermore, there is a need for establishing theoretical foundations and frameworks for meta-learning to better understand the underlying principles and ensure the reliability and scalability of these techniques in practical applications. It's important to have a solid theoretical basis to guide future developments in meta-learning. Now let's talk about the potential future applications and impact of meta-learning. The possibilities are vast and could revolutionize various fields. In healthcare, for example, meta-learning can be employed to develop personalized treatment plans for patients based on their clinical data, resulting in improved patient outcomes and reduced healthcare costs.
And in the field of education, meta-learning can enhance adaptive learning systems by helping students navigate through vast amounts of information and tailor their learning experience according to their individual needs. This can greatly improve the effectiveness of education and make learning more personalized. Moreover, meta-learning has the potential to greatly impact the field of autonomous systems. By leveraging meta-knowledge, autonomous vehicles can adapt to various driving conditions and learn from their experiences, leading to safer and more efficient transportation.
Absolutely, Avery. In the realm of finance, meta-learning algorithms can assist in predicting market trends, making informed investment decisions, and optimizing portfolio management strategies. This has the potential to greatly improve financial decision-making and increase profitability. Overall, the potential future applications of meta-learning are extensive and promising. It positions meta-learning as a transformative technology across different domains.
That's right, Ben. Meta-learning has the power to revolutionize various industries and contribute to the development of more intelligent and adaptive systems.
To sum up, meta-learning is a crucial technique for improving the performance and efficiency of machine learning models. It enables models to learn from past experiences and adapt quickly to new tasks. However, there are still challenges to be addressed and further research is needed to fully unlock the potential of meta-learning. Absolutely. Meta-learning techniques have the potential to enhance the efficiency and effectiveness of machine learning techniques in various domains. They enable machines to learn how to learn, making them more adaptable and flexible.
Now let's dive into the different types of meta-learning techniques. There are three main categories: model-agnostic, model-based, and metric-based methods.
Model-agnostic methods aim to learn optimal initialization strategies that can be applied across different learning algorithms and models. They focus on discovering generalizable knowledge about learning, such as which architectures, hyperparameters, or optimization algorithms work best.
That's right. Examples of model-agnostic methods include model-agnostic meta-learning, MAML, and cross-validation-based meta-learner, CVML.
On the other hand, model-based techniques aim to learn a surrogate model that captures the relationship between different learning tasks and their corresponding models. They leverage the knowledge gained from previously encountered tasks to guide the learning process for new tasks.
Popular examples of model-based meta-learning techniques are reptile and Bayesian optimization-based meta-learning, BOML.
Lastly, metric-based methods employ distance metric learning to define the similarity or dissimilarity between different tasks. By discovering shared characteristics across tasks, these approaches can effectively transfer knowledge between them.
Prototypical networks and matching networks are examples of metric-based meta-learning techniques.
These diverse types of meta-learning techniques provide valuable tools for enhancing the efficiency and effectiveness of machine learning models and algorithms. It's fascinating to see how different approaches can be used to tackle different challenges.
Definitely. Now let's focus on model-agnostic meta-learning. This approach, also known as transfer learning, has gained significant attention in recent years.
That's right. Model-agnostic meta-learning involves training a meta-learner on multiple tasks with different models and datasets, aiming to learn a set of high-level features that can be generalized to new tasks.
One advantage of model-agnostic meta-learning is that it does not rely on assumptions about the specific model architecture or underlying data distribution. Instead, it focuses on extracting universal knowledge that can be applied across models and datasets.
And this versatility makes it particularly useful in scenarios where the availability of labeled data is limited or when the models used in the training process are diverse. Model-agnostic meta-learning has the potential to significantly improve the performance of machine learning models in a wide range of applications.
Absolutely. It's an exciting approach that opens up new possibilities for machine learning. And with continued research and development, we can expect even more advancements in the field of meta-learning.
That's right. One of the key areas of meta-learning is model-agnostic meta-learning, which focuses on developing algorithms and approaches that can be applied across different machine learning models. The goal is to transfer knowledge from one model to another without assuming any prior knowledge about the specific model being used.
That's an important point. The algorithms in model-agnostic meta-learning are designed to learn a generic representation of a problem and its solution. This allows for the adaptation and transfer of knowledge to different models. Some popular techniques used in model-agnostic meta-learning include gradient-based methods, such as MAML and reptile. These approaches optimize the initialization of the model's parameters, enabling efficient knowledge transfer and rapid learning in new tasks and domains.
Gradient-based methods like MAML are particularly powerful because they use gradient descent to update model parameters based on multiple tasks. This allows for fast adaptation to new tasks with minimal training data. Reptile, on the other hand, focuses on higher-level network structures and performs a similar update process.
That's correct. By optimizing the initialization rather than the model directly, MAML and reptile allow for improved generalization and fast adaptation to new tasks. This makes them valuable tools for addressing the challenges of learning in complex and dynamic environments.
Absolutely. Now let's talk about memory-based meta-learning, another type of meta-learning technique that has gained popularity in recent years. In this approach, a neural network architecture called a memory-augmented neural network is used to store and retrieve information about previously encountered tasks.
That's right. The memory module comprises a set of key-value pairs, where the keys are representations of the tasks and the values are representations of the solutions or optimal performance for those tasks. During training, the network learns to use this memory to quickly adapt to new tasks by querying the memory for relevant information.
This memory-based approach allows the network to generalize knowledge across tasks and efficiently learn new ones. It's particularly useful when there is limited labeled data or limited computational resources, as it enables the learner to make more efficient use of available resources and improve performance on new tasks.
Exactly. Memory-based meta-learning leverages prior knowledge and experience stored in the memory module to aid in the learning of new tasks. This approach enhances the ability of models to adapt to new tasks and improve overall performance.
And there are different algorithms and approaches used in memory-based meta-learning. One popular algorithm is the k-nearest neighbors, KNN algorithm. It finds the k-nearest neighbors to a given query instance and uses the stored information associated with these neighbors to make predictions or guide the learning of a new task.
Another approach is the use of support vector machines, SVMs, in meta-learning. SVMs can be trained to learn similarity measures between tasks and use this information to assist in the learning process. Additionally, memory-based meta-learning can incorporate different memory structures, such as lookup tables or neural networks, to efficiently store and retrieve information.
These algorithms and approaches in memory-based meta-learning contribute to the adaptability and performance of machine learning models. They allow models to leverage past experiences and knowledge to quickly adapt and learn new tasks, even with limited data or computational resources.
Absolutely. The combination of model-agnostic meta-learning and memory-based meta-learning opens up exciting possibilities for the field of machine learning. These techniques enable rapid learning of new tasks, efficient knowledge transfer, and improved generalization in complex and dynamic environments.
And with further research and development, we can expect even more advancements in these areas. Meta-learning is a rapidly evolving field, and these techniques have the potential to revolutionize the way we approach machine learning problems.
That's right. One approach to meta-learning that we want to highlight is optimization-based meta-learning. This technique focuses on optimizing the learning process itself. By using optimization algorithms, the algorithm is able to find the optimal set of parameters for a learning algorithm based on past experience.
The main advantage of optimization-based meta-learning is that it can adapt the learning algorithm to specific tasks and datasets, leading to improved performance and generalization. This is because it takes into account the learning process itself, allowing for more efficient and effective machine learning models.
One popular optimization-based meta-learning algorithm is called model-agnostic meta-learning, or MAML for short. MAML aims to find a good initialization of the model parameters that can quickly adapt to different tasks. It does this by iteratively updating the model parameters based on how well it performs on a set of tasks sampled from a task distribution.
By explicitly considering the learning process in the meta-learning framework, optimization-based meta-learning provides a powerful tool for improving the efficiency and effectiveness of machine learning models. It allows the algorithm to better learn how to generalize and transfer knowledge from one task to another.
In terms of the algorithms and approaches used in optimization-based meta-learning, gradient-based methods are widely used. These methods aim to optimize a model's parameters by computing gradients of the empirical risk with respect to those parameters.
The most commonly used algorithm in this category is stochastic gradient descent, SGD, which updates the parameters iteratively based on many batches of data. Another approach is the atom optimizer, which combines the advantages of both RM, SPRUP, and momentum methods to adaptively adjust the learning rate.
Other optimization algorithms like conjugate gradient and quasi-Newton methods have also been employed in meta-learning frameworks. However, these approaches often require careful tuning of hyperparameters and may suffer from slow convergence or getting stuck in local optima.
Despite these challenges, optimization-based meta-learning algorithms offer powerful tools for discovering effective learning strategies and adapting models to new tasks efficiently. They have shown promise in many domains, including computer vision, natural language processing, and robotics.
Absolutely. Optimization-based meta-learning has the potential to enhance the performance of machine learning models across a wide range of practical settings. It allows for rapid adaptation to new tasks, improved generalization, and efficient knowledge transfer.
And it's not just about improving traditional machine learning techniques. Meta-learning also offers new approaches to improving the overall performance and generalization of machine learning algorithms. One such approach is using the performance of different algorithms on a range of tasks as input to train a meta-learner.
Another technique is using meta-features, which are high-level representations of the data or algorithms, to guide the learning process. These meta-features can capture important characteristics that help select the best approach for a given problem.
Overall, meta-learning provides a promising direction for further improving the effectiveness and efficiency of machine learning algorithms. It has found applications in various domains such as natural language processing, computer vision, and reinforcement learning.
In natural language processing tasks like machine translation and sentiment analysis, meta-learning allows models to quickly adapt to new languages or domains, improving their performance in specific tasks.
And in computer vision tasks like image classification and object detection, meta-learning algorithms enable models to transfer knowledge across different datasets and adapt to new visual environments.
Additionally, in reinforcement learning, meta-learning has proven effective in optimizing the learning process by adapting the policy or value function.
So as we can see, the applications of meta-learning are wide-ranging and have the potential to enhance the performance of machine learning models in various practical settings.
That's right. One particular area where meta-learning has shown great promise is in computer vision. Computer vision tasks like object recognition and image segmentation typically require large amounts of annotated data to achieve high accuracy. However, collecting and annotating this data can be time-consuming and costly.
That's where meta-learning comes in. Meta-learning approaches leverage prior knowledge acquired from related tasks to facilitate faster learning of new tasks. For example, a meta-learning algorithm can learn generalizable representations or optimization strategies that can be transferred to new tasks, reducing the need for extensive data collection and annotation.
This is particularly useful in object recognition and classification. By using meta-learning, computer vision systems can learn to recognize and classify objects more efficiently and effectively. Meta-learning algorithms allow the models to adapt and generalize across different tasks and datasets, enabling the system to learn quickly and make accurate predictions on new and unseen data.
And it's not just about efficiency. Meta-learning also allows models to learn from limited labeled data. With few labeled samples, meta-learning algorithms can leverage the knowledge gained from previous tasks and transfer it to new tasks, improving performance and reducing the need for extensive labeling. This is especially valuable in scenarios where data acquisition and annotation are costly and time-consuming.
Absolutely. Meta-learning has already found successful applications in various fields. For example, in computer vision, meta-learning has been used to improve object detection and recognition tasks. By training the meta-learner on a large dataset of images with labeled objects, it can quickly adapt to new image datasets and achieve high accuracy in object identification.
That's not all. Meta-learning has also shown promising results in natural language processing, NLP, specifically in machine translation. By utilizing meta-learners, neural machine translation models can be adapted to different language pairs, resulting in improved translation quality.
And let's not forget about reinforcement learning. In this field, where an agent learns to interact with an environment to maximize a certain reward, meta-learning can be incredibly useful. By using meta-learning, the agent can quickly adapt its learning strategies to new tasks, improving the efficiency and effectiveness of the learning process.
So as we can see, the versatility and effectiveness of meta-learning techniques in solving complex problems across various domains are evident. It's not just limited to computer vision or NLP, but can be applied in reinforcement learning in other fields as well.
That's a great point, Ben. And speaking of NLP, meta-learning has also found significant applications in this field. Traditional approaches in NLP often depend on extensive human annotation and domain-specific feature engineering, making them highly reliant on labeled data availability.
That's where meta-learning comes in to revolutionize the field. With meta-learning techniques, NLP models can learn from previous experiences and generalize across tasks and domains. Meta-learning in NLP focuses on learning to learn across different language tasks like sentiment analysis, machine translation, and named entity recognition.
By utilizing meta-learning, NLP models can dynamically adapt to new tasks and transfer knowledge from one task to another. This allows for more efficient and effective learning in the field of natural language processing.
Absolutely. Incorporating meta-learning techniques in language processing models can greatly enhance their performance and adaptability. Meta-learning involves training a model to learn the intricacies and patterns of a given language, allowing it to generate more accurate and contextually appropriate text.
Incorporating meta-learning techniques allows language processing models to dynamically adjust their parameters and strategies based on the specific task or dataset at hand. This not only improves their performance on common language processing tasks like machine translation or text summarization, but also enables them to transfer knowledge across different domains or languages.
And let's not forget the challenges that meta-learning can help overcome. Meta-learning in language processing can assist in overcoming challenges such as data scarcity or domain shift, where models struggle to generalize to new or unfamiliar data.
Overall, the integration of meta-learning techniques in language processing models holds significant potential to advance the field and enhance the capabilities of language processing technology. Absolutely. One of the primary improvements achieved through meta-learning is the ability to adapt to new tasks and domains with minimal or no additional training data. By leveraging knowledge gained from previous tasks, meta-learning enables NLP models to learn more quickly and effectively.
However, there are still several challenges that need to be addressed. Firstly, the selection of an appropriate meta-learning algorithm is critical. Different algorithms may perform better depending on the nature of the task and the data, so finding the right algorithm for a specific task is crucial for optimal performance.
That's right. Another challenge is the lack of a standardized evaluation methodology for comparing different meta-learning techniques. Without a standardized way of evaluating these techniques, it becomes difficult to determine which ones are more effective or efficient.
And let's not forget about catastrophic forgetting. This is when knowledge of previous tasks is lost when learning new tasks. It's a significant challenge because it hinders the ability of models to transfer knowledge effectively.
Absolutely. Addressing these challenges and further refining meta-learning techniques in NLP will undoubtedly lead to improved performance and more robust models.
Now let's talk about how meta-learning in reinforcement learning works. Meta-learning in reinforcement learning refers to the ability of an agent to learn how to learn in the context of reinforcement learning tasks. The goal is to enable an agent to quickly adapt to new tasks by leveraging prior knowledge and experience gained from similar tasks.
That's correct. Meta-learning algorithms in reinforcement learning typically involve learning a high-level policy or a set of meta-parameters that guide the learning process. These algorithms aim to optimize the agent's ability to generalize across different tasks and effectively use previously learned knowledge to expedite learning in new tasks.
And this approach has shown promising results in various domains, including robotics and game playing. By enabling agents to learn more efficiently and achieve higher performance on new and unseen tasks, meta-learning in reinforcement learning has the potential to revolutionize these fields.
Absolutely. Now let's talk about how meta-learning enables faster learning in reinforcement learning. One technique that has shown promising results is the extraction of task-specific features and learning algorithms. By capturing knowledge learned across multiple tasks, meta-learning provides a more generalized understanding of the underlying patterns and structures within a given environment.
That's right. This generalized understanding allows the agent to make better decisions and optimize its learning process. Meta-learning also offers the advantage of being able to adapt quickly to new tasks and transfer knowledge from one task to another. Overall, it enhances learning speed by leveraging previous knowledge and experiences.
Now let's discuss some case studies and advancements in reinforcement learning using meta-learning. One notable case study is the use of meta-learning to optimize the performance of robotic grasping tasks. By leveraging meta-learning techniques, robots can quickly adapt to novel objects and grasp them with higher success rates.
Another case study involves improving the efficiency of neural architecture search, NAES, using meta-learning. By utilizing meta-learned priors, the search space for finding optimal neural network architectures can be significantly reduced, leading to faster and more accurate NAES.
And advancements in RL using meta-learning have been achieved by incorporating model-based methods. By learning the dynamics of the environment, meta-learning algorithms can effectively plan and optimize policies, resulting in superior performance in complex tasks.
These case studies and advancements highlight the potential of meta-learning in enhancing RL algorithms and pushing the boundaries of artificial intelligence.
That's right. Meta-learning is a subfield of machine learning that focuses on using machine learning algorithms to learn how to learn. It aims to develop models and techniques that can automatically learn from previous learning experiences and adapt to new learning tasks more efficiently.
Exactly. Meta-learning involves learning higher-level knowledge or representations about learning itself. Instead of focusing solely on solving specific learning problems, meta-learning focuses on developing a more generalized understanding of the learning process.
One common approach in meta-learning is to use meta-features, which are extracted from the dataset or the learning algorithm, to provide information about the characteristics of the problem and guide the learning process.
Another approach is to learn a meta-learner that can discover and exploit structural patterns in the input data or the learning algorithm to make better predictions or decisions.
Overall, meta-learning plays a crucial role in pushing the boundaries of machine learning by enabling systems to leverage their previous learning experiences to enhance their performance and adaptability.
Absolutely. However, there are some limitations and challenges that we need to be aware of when it comes to meta-learning. One major limitation is the issue of transferability. While meta-learning algorithms are designed to learn knowledge and skills from one task and apply them to another, the transferability of learned information is not always guaranteed.
That's right. The success of transfer often relies on the similarity between the tasks being learned and the tasks being applied to. If the tasks are too dissimilar, the learned knowledge may not be applicable or beneficial in the target task. So it's important to consider the similarity between tasks when applying meta-learning techniques. Another challenge is that meta-learning algorithms often require a large amount of training data to effectively generalize across tasks. This can be quite challenging in scenarios where only limited or sparse data is available. The efficacy and performance of meta-learning techniques heavily rely on the availability and similarity of the training data, which can be a significant limitation and obstacle in practical applications.